Hello everyone, myself Dr. Amit Kumar Yadav, Associate Professor, School of Computer Science and Artificial Intelligence, SR University, Warangal, Telangana, India. Today we are going to see unlocking time series secret from data to decisions. First we will see here what is time series data. Imagine a story told over time, a patient heart climbing, a stock price falling, or the temperature shifting hour by hour. So here time series data is simply a sequence of data point collected over a period. The golden rule, orders matters. Shuffling the data destroy its meaning. Unlike a spreadsheet rows, each point depends on what came before it. So we can say here time series data is simply a sequence of values recorded over time. For example, think of temperature changes, stock prices, or a patient heart rate. And here's the golden rule, order matters. If you shuffle the data, you lose the story completely. Why is time series data special? Trend. Long-term rise or fall, example, global temperature increasing decades over decades. Seasonality, regular repeating patterns, example, ice cream sales spike in every summers. Cycles, longer, irregular ups and downs, example, economic booms and bust cycles. Noise, random fluctuation that hides. In another word, we can say here time series data has unique patterns. Trend means long-term movement. Seasonality, repeating patterns. Cycles, irregular up and downs. Noise means random fluctuation. Our job is to separate meaningful patterns from noise. Basic technique for understanding time series. Before diving into advanced AI models, it helps to master the foundational tools, the building block every data scientist relies on. So we can say here, before advanced AI models, we start with simple but powerful technique. Technique one, simple moving average. It is called as SMA. Simple moving average smooth out noise, so the underlying trends become visible. It calculates average of fixed windows of recent data point, then slide that window toward one step at a time. Analogy, like slightly blurring a shaking photo. The final noise disappears, revealing the main subject clearly. Example, average daily stock prices over the 7 days. In another word, we can say here simple moving average smooths out noise. It averages the fixed windows of data point to reveal trend. Think of it like slightly blurring an image. The distraction fade and the main patterns become clear. Exponential smoothing. How it is different from SMA, that is simple moving average. Instead of treating all past points equally, exponential smoothing gives more weight to recent data. The influence of older observations shrink exponentially, meaning yesterday matter more than last month. Analogy: you pay more attention to today news headlines than a story from 6 months ago. Use case: forecasting short-term sale figures based on, say, most recent performance trade. So simple moving average, it gives equal weight to all points in the windows. Exponential smoothing. Here, unlike SMA, exponential smoothing gives more importance to recent data because in real life, yesterday data often matter more than last year. This makes it very useful for short-term forecasting. Why sequence when sequence don't line up? Dynamic time wrapping. What happens when two time series tells the same stories but at different speed? Standard comparison breakdown. DTW is the solution, that is a dynamic time wrapping. Now let's look at a challenge. What if two sequences are similar but happens at different speeds? The problem: different speed, same patterns. Why simple comparison fails? Imagine two people singing the same song, but one sings faster. If you compare them note by note at the same moment in time, they won't match, even though the melody is identical. This is a real challenge when comparing ECG signals from two patients with slightly different heart rate or speech recording of the same word spoken at different speeds. Point by point comparisons assume perfect time alignment, an assumption that rarely holds in real world. Here it is called as misaligned signal, it is called as name comparison errors. In another word, we can say that imagine two people singing the same song, one faster than the other. If we compare them point by point, they look different, but the pattern actually the same. This is where normal comparison fails. Dynamic time wrapping DTW to the rescue. What it is? It means a clever algorithm which is used to compare two time series by wrapping the time axis of one to best match the other. How it works? It finds optimal aligned path through a cost matrix, stretching or compressing section as needed. The analogy: like stretching or compressing a rubber band to make two patterns perfectly. The result measure true similarity even when timing is imperfect. So we can say here dynamic time wrapping solve this. It stretches up compresses time to align two sequences properly. Think of it like stretching a rubber band to make two patterns. This helps us measure true similarities. Making sense of complex model time sap. Powerful AI model can make accurate prediction, but often without explaining themselves. Time sap changes that. The black box problems. When model can't explain themselves. Deep learning models like LSTMs, transformers achieve remarkable accuracy on time series tasks, but they are notoriously hard to interpret. We see prediction, but not why the model arrived at. Analogy it's like magic trick. The rabbit appear, but the mechanism is hidden. In high stakes domain like healthcare, finance, trust me is not enough. SAP fairly distributing credit. Rooted in game theory, SAP, Shapley Additive X platform borrows from cooperative game theory to fairly assign credit for a prediction across all input features. It considers every possible combinations of features to determine how much each one truly contribute, ensuring no features takes under deserved credit. Analogy if a team win a match, SAP calculate exactly how much each individual player contributed to that victory, fairly not just by who scored last. SAP is a method based on game theory. It fairly assigns credit to each feature for a prediction, like figuring out how much each player contribute to winning a match. Time SAP, SAP for time series. The adoption. Time SAP extends SAP to handle unique structures of sequential data. When time steps, not just features, need to be explained. What it reveals. It identifies which time series in the input sequence were most critical to model prediction, giving us a temporal map of importance. Why it matters. Build trust in AI system by showing exactly what the model looked at and before making its decisions, especially valuable in medical and financial applications. So we can say here time set adopts SAP for time series. Instead of just features, it tells us which time steps were important. This helps us understand when the model focused its attentions. Visualizing model decisions saliency map. What if we could see exactly when an AI looked when making a decision? Saliency map makes invisible visuals. In another word, we can say that saliency map highlights the most important part of input. They show where model is looking. Bright area means high importance. What are saliency maps? Highlight what matters. We can say here saliency maps are visual tools that highlights the most important part of input data for model predictions. They work by computation of gradient, means measuring how much a small change in each input point shift the output. High gradient is equal to high importance is equal to highlighted on the map. So we can say here saliency map highlights important part of the input. They show where the model is looking. Bright area means high importance. Saliency map for neural network. Why recurrent neural network need this? RNN are powerful for sequence, but their internal memory make them hard to interpret. Saliency map expose which past input most influence the current prediction. Text prediction example. In a text prediction, RNN saliency maps highlight the specific word that drove the next word suggestion, making the models reasoning visible. Medical application for EGC saliency is used. For examples, in text predictions, important words are highlighted. In ECG analysis, important signal segments are marked. This makes AI decisions more transparent. Advanced explanation beyond the time domain. Sometimes the most important patterns are not visible in time. They are hiding in frequency, scale, or other mathematical transformation of the signals. Cross-domain integrated gradient. Looking beyond time, this technique extends the classic integrated gradient method to analyze time series in multiple domains, not just time, but also frequency. Example via Fourier transform and other invertible representation. By examining signal through different mathematical lenses, it can reveal patterns that are completely invisible in the raw time domain. Benefit: uncover hidden insights like subtitle rhythms in heart rate variability that only appears in frequency domains. This method analyzes data in multiple domains like frequencies. It helps uncover hidden patterns that are invisible in raw data. Binstep window temporal saliency rescaling. What makes it different? Standard saliency map treat each time step independently. Binstep bin TSR recognized that in real sequence What happens three steps ago may be just as revealed as what happened last step. However, scale importance is scored based on major temporal dependencies within sliding windows. Benefit produce more accurate dynamic explanation for complex. So we can say here when TSR improves on standard saliency by explicitly accounting for how time steps influence each others, not just the outputs. The futures of time series understandings foundation SMA and exponential smoothing reveal trend hidden in noisy data alignment. DTW compares sequences that vary in speed, unlocking true similarity. Explainability, time shape, and saliency map make black box model transparent and trustworthy. Frontier, cross-domain and bench-type method pushes explanation into new dimensions. The ability to understand time series data is one of the most powerful skills in today's uh, driven world. Keep exploring. The next big insights might be hidden in sequence, waiting for to understand. Unlocking the way a journey into causal reasoning. From correlation to causation, a student-friendly guide to the most powerful ideas in modern data science. What is causality? Beyond correlations, we observe patterns everywhere in data, in life, in system. But here's the key questions. Do these patterns actually mean one thing causes another? Causal reasoning helps us more from simple observation to true understanding. So we can say that it includes observations, questions, the missions. Observation means we notice patterns and relationship in data around us every day. Questions what this pattern means. Mission causal reasoning help us move from noticing to truly understanding. Correlations versus causation. The classic mix-up. Correlation, causation. Correlation two things happen together. Ice cream sale and crime rate both rise in summer. But ice cream doesn't cause crime. A hidden factor, hot weather, drive both. Causation. One thing make another happen. Turning a key causes the car to start. Mistaking correlation for causation leads to costly, dangerous decisions. Why causality matters? Causality is important because it helps us understand how systems really work, make better decisions, predict what happens if we change something. For example, does a medicine cure a disease? This is a causal question. Causal interference inference techniques. It means finding the true values in a full of noise, hidden variables, and misleading patterns. Now the challenge is how do we find true causes in many real world. The challenge is unseen factors, confounders, the studies and great problem. We want to know does study more cause better grade? A confounder like a better teachers or natural ability affect both study times and grade, making it hard to isolate the real effect. For this, we need smart techniques to separate true cause. We can say here, co-founders are hidden variables that affect both cause and outcomes. For example, does study improve grade? Or is it intelligence or teaching quality influence both? These hidden factors make causality difficult to identify. Randomized controlled trial, the gold standard. Randomization balances all confounders on average, making RCTs the most reliable tool. The catch. We randomly assign pupils to group, treatment and controls. This balance confounders and give reliable result, but not always practical or ethical. Observational studies. In many cases, we cannot run experiment, so we rely on observational data. Here we use static methods like matching and regression to control confounder through its more challenges. Causal mediation analysis. It's not just about whether X causes Y, it is about how and why the effect travel from cause to outcome. Does X causes Y? Understanding the pathway. Consider these examples. Exercise increase metabolism, weight loss. The mediator metabolism explain how the effect has happens. So here a treatment here X denoted by new exercise program, outcome weight loss. Mediators increase metabolism. The exercise program cause a rise in metabolism which in turn cause weight loss. The mediator is the mechanism carrying the effect. Direct versus indirect effect. Natural direct effect. The effect of X on Y bypass the mediator entirely. Does exercise cause weight loss? Through other pathway beyond metabolism. Natural indirect effect. The portion of the effect that flows through the mediator. How much weight lost is explained specifically by the metabolism by metabolic boost. Total effect. The complete picture T is equal to Nd plus Ni Understanding both parts give a fuller, more actionable view of causation. Distangle representation for meditation analysis. Why go deeper? In complex systems, hidden variables exist. Modern deep learning techniques help uncover these hidden influences, improving causal analysis. Invariant risk minimization. Building machine learning models that are robust, one that work not just on training data, but in real messy world. So here invariant risk minimization or IRM solve this. It finds the problem, the model that don't generalize. Generalization problem. Machine learning models sometimes learn wrong pattern. For example, a model may associate spiders with green background instead of learning what a spider actually look like. This is called spurious correlation. IRM the idea. Invariant risk minimization or IRM solve this. It finds features that remain consistent across different environments. Two causal relationships don't change with context, and that what IRM focuses on. Causal discovery can be automatically discover causal relationship from the data. From data to causal graph, causal discovery algorithm but a map of cause and effect relationship. They analyze dependencies between variables to construct a causal graph. Latent variables in real world data, not everything is observed. Some factors remain hidden. Advanced models combine deep learnings and probability to uncover the latent variables. Structural causal models. Now we reach one of the most powerful networks in casualty. Structural causal models developing by, say, GDOPL structural causal model provide a complete language causality. They include variables, causal graph, mathematical relationship, and most importantly, they allow us to answer what happened if we intervene. What would have happened under different conditions? These are called intervention and counterfactuals. The core of true cause reasoning. So we can say that causal reasoning transforms data into understanding. It allows us to move beyond patterns and uncover the true mechanism behind the world. And in doing so, it gives us the power to make better, smarter decisions.